I want you to picture a scene in a chemistry lab. It's a standard practical class. Maybe it's a Tuesday afternoon.
Okay.
You're standing there with a test tube, and inside there's some water. You take a dropper and carefully add a few drops of aniline.
Aniline, right.
Yeah.
That oily yellowish liquid.
Exactly. And just like, cooking oil in a glass of water, it just refuses to mix. It just floats there, sitting separately.
It's a stubborn emulsion. It just won't dissolve.
It won't. But then, and this is the part that always looks like a magic trick, you add a few drops of concentrated hydrochloric acid. You give the test tube a little shake, and suddenly the oil is gone.
Just like that. The solution becomes crystal clear.
Completely dissolved. But the trick isn't over yet, is it?
No, it's not.
Because if you then take a base like sodium hydroxide and add it to that clear solution,
Yeah.
boom, the oily aniline comes right back.
Out of nowhere. It precipitates, and the oil floats to the top again.
It vanishes, then it reappears like a ghost. So the question we're starting with today is, why does it do that? What is happening on the molecular level to make an oil suddenly love water and then hate it again?
It's a beautiful demonstration, isn't it? And while it looks like magic, it is actually the perfect doorway into our topic today.
It's not a trick, it's chemistry.
It is the fundamental behavior of nitrogen.
Welcome to the deep dive. Today we are opening up Unit 9, Amines. We have combed through the textbooks, the research, and your revision notes to crack the code on the chemical reactions of amines.
And frankly, this is one of those topics in Class 12 that acts as a gatekeeper. If you understand this, organic chemistry really starts to make sense.
And if you don't?
It remains a list of random equations you just have to memorize.
Right. And looking at the sources we have, the mission today is pretty clear. We aren't just reciting reactions. We want to get to the point where you can predict the product.
And understand how we go from a beaker of liquid to making materials like, say, nylon.
And fundamentally, understanding why amines are kind of the social butterflies of the functional groups.
That's a great way to put it. They interact with everything, unlike alcohols or ethers, which are a bit more reserved.
So let's strip this down. I want to start at what we call the zero level, the absolute simplest explanation. When a student looks at the syllabus, they see acylation, alkylation, diazotization. It looks like a huge disconnected list.
It does. It's intimidating.
Is there one single engine driving all of this?
Yes. And this is the secret to the whole chapter. You can, throw away the list if you just remember one thing.
Yeah.
Every single chemical reaction of amines happens because of two key properties. Amines act as bases, and they act as nucleophiles. That's it.
Bases and nucleophiles. Okay, let's visualize this because those words get thrown around a lot in class.
Mm-hmm.
I want everyone listening to close their eyes for a second. Picture the nitrogen atom in an amine molecule. It's sitting there, bonded to some carbons or hydrogens, but it has this one special feature, a lone pair of electrons.
Think of that lone pair as a hand.
A hand. I like that.
It's a hand sticking out from the nitrogen, and it is negatively charged. It is electron-rich.
So, because it's rich.
It's desperate to share that wealth. It is always reaching out, ready to grab something positive.
So the hand is the engine. Now, distinguish the two roles for me. When is it a base, and when is it a nucleophile?
It depends entirely on what the hand grabs.
Yeah.
If that hand reaches out and grabs a hydrogen ion, H+, then the amine is acting as a base.
Like catching a small ball.
Exactly. The proton is a tiny positive ball. The hand just catches it. That is your classic acid-base reaction.
Simple enough.
But if that same hand reaches out and attacks an electron-deficient carbon atom, say, a carbon that's feeling a bit positive because it's attached to a halogen, then the amine is acting as a nucleophile.
Okay, so the hand, the lone pair, is the exact same thing in both cases. The action is the same.
Yeah.
Grabbing. It's just the target that changes.
Precisely. If you grab a proton, you are a base. If you attack a carbon, you are a nucleophile. The electrophile changes, but the nature of the lone pair, that grabbing tendency, stays the same.
That simplifies things massively. So if we need to put this into an exam-safe definition, what is the anchor sentence we should keep in our heads?
If you are writing an answer in the boards, here's your anchor. Chemical reactions of amines involve the lone pair on nitrogen acting as a nucleophile or base, including protonation, acylation, alkylation, oxidation, and diazotization.
Lone pair acting as a nucleophile or base. That's the mantra.
That's it.
But here is where it gets a bit tricky, and I see students trip up on this all the time. You look at a molecule, you see a nitrogen, you see a lone pair, and you assume, okay, All amines must react the exact same way.
The one-size-fits-all trap, it's a very dangerous assumption in organic chemistry. You think, I see the hand, it grabs.
But you have to remember we have different categories now.
We do. We have primary, secondary, and tertiary amines.
The 1 degree, 2 degree, and 3 degree amines.
Correct. And they react very differently, not because the hand disappears, but because of the environment around the hand. We call this steric hindrance.
Steric hindrance, that's the academic way of saying crowding, right?
Exactly. Go back to our analogy. In a primary amine, the nitrogen is attached to only one carbon chain. There's plenty of open space around the hand.
The hand is free?
It can reach out and grab things easily, but in a tertiary amine, you have 3 big, bulky alkyl groups crowding around that nitrogen.
Okay, so it's blocked.
It's like trying to shake hands with someone while you are wearing a giant puffy winter coat and they're wearing one too. You physically cannot get close enough.
Or like trying to reach for a snack when you're sitting in the middle seat of a crowded car. You have the hand, you want the snack, but you just can't make the move.
That is a perfect way to put it. The desire to react, the electronics is there, but the geometry, the sterics, says no.
And there's another factor too, isn't there? The hydrogens.
Yes. Plus, there's the factor of hydrogen bonding. Primary amines have 2 hydrogens attached to nitrogen that can be replaced. Secondary have 1, tertiary have none. This drastically affects what products they can form.
Okay, so let's build on this hand analogy. I want to walk through the specific reactions in the syllabus using this mental model.
Good idea.
We established that grabbing a proton, the tiny ball, is the acid-base reaction.
Right. And that is the easiest one. That's scene 1.
Now let's look at acylation. The source material mentions reacting an acid bondman with an acyl chloride. What is the hand grabbing here?
Think of an acyl group, that C double bondo group, as a hook, a very sharp hook.
A hook.
The lone pair reaches out and grabs this hook. But unlike the proton ball, which just sits in the hand, the hook transforms the amine entirely. You aren't just holding it, you become an amide.
So grabbing a ball gives you a salt. Grabbing a hook gives you an amide. Now what about alkylation? This is where we react with an alkyl halide.
In alkylation, let's think of the alkyl group as a heavier ball, maybe a medicine ball. The hand grabs it, but in doing so, it has to drop one of its hydrogens.
So you're adding carbon chains to the nitrogen.
You are.
But wait, if I add a carbon chain, I've just turned a primary amine into a secondary amine.
Exactly. And this is the danger zone.
And a secondary amine still has a lone pair. It still has a hand. So you can grab another ball.
You have hit on the big problem with alkylation. Yes, it can. In fact, the secondary amine is often more eager to grab another ball than the first one was.
So it grabs another. Now it's tertiary.
And it can grab another. It becomes a quaternary ammonium salt.
So the hand is basically hyperactive. It just keeps grabbing until it's completely overloaded.
It's a runaway reaction. It's very hard to stop at just one step. That's why alkylation often gives you a messy mixture of products.
Whereas acylation
Is cleaner because the hook shuts down the reactivity a bit.
That is a crucial distinction. Alkylation is messy. Acylation is controlled. Why do we even care about this, though? I mean, apart from passing the exam.
It's a fair question. Look, if we didn't understand this nucleophilic nature, this grabbing ability, we couldn't design medicines. We wouldn't be able to make amides.
And amides are the backbone of proteins.
Exactly. We wouldn't be able to make polymers like nylon or Kevlar. It's the toolbox for building modern materials.
Without this concept, organic chemistry would just be
alchemy, mixing things and hoping. The lone pair concept explains why the reactions happen, which lets us engineer new ones.
I want to try a mental movie here. I love these because they really stick in your head during the exam when you're staring at a blank page.
Sure, let's do it.
Can you guide us through the reaction landscape?
Okay, close your eyes again. Visualize a nitrogen atom floating in the dark. It's at the center of a sphere. Now, see that lone pair? Imagine it as a glowing orange or red electron cloud extending outwards.
Like a balloon made of light.
A glowing orange balloon. Got it. Scene 1. Protonation. A tiny blue sphere, that's the proton, comes floating by. The orange cloud just engulfs it. Snap. They connect. The glow changes color because the charge is neutralized. That is your acid-base reaction.
Easy. Scene 2.
Scene 2. Acylation. Now, a bigger, more complex group approaches. It has a double bond to oxygen. It looks angular, sharp.
Right.
The orange cloud attacks the central carbon of this group. As it connects, it pushes away a leaving group, let's say a green sphere representing chlorine.
Okay, the green sphere flies off.
It flies off into the darkness, and the nitrogen is now permanently fused to this new group.
That's the substitution. And scene 3. This is the tricky one.
This one is special, diazotization. But remember, this is for aromatic amines only, like aniline.
Right. And it has to be cold.
Ice cold, 0 to 5 degrees Celsius. A nitrifying agent approaches. The reaction is chaotic. The amino group transforms. It becomes a vibrating, rigid, stick nitrogen, triple bonded to nitrogen with a positive charge.
N triple bond, yeah.
It's vibrating. It's unstable. It looks like it wants to explode, and if you let it warm up, it will. But for now, the ring holds it in place. That is the diazonium salt.
Vibrating and unstable. That's a great image because we know diazonium salts are super reactive intermediates.
They are like a loaded spring.
Then loaded spring is what allows us to swap that nitrogen group for almost anything else, isn't it?
Exactly. A halogen, a cyanide, a hydroxyl group. It's the ultimate swap shop of chemistry.
Let's bring this back to the real world.
No.
We started with that magic trick of aniline dissolving in acid. Can we explain that now using our hand analogy?
Yes. So aniline is that oil. It's organic, nonpolar. It hates water, but it has the hand, the lone pair. When you add acid, HCl, there are millions of protons, H+, swimming around.
The tiny blue balls from our movie.
Right. The hand grabs a proton. Now, the aniline isn't aniline anymore. It becomes the anilinium ion. Crucially, it now has a positive charge.
What do we know about charged things in water?
They love each other. Charged things are soluble, so the oil vanishes because it has turned into a salt, specifically anilinium chloride, which dissolves perfectly in water.
But then when we add the base...
The base comes in, usually OH-, and it is a stronger bully. It steals the proton back from the nitrogen.
The hand is empty again.
Correct. The aniline loses its charge, becomes neutral, becomes oily again, and precipitates out.
That is so clear now. It's just a game of catch with a proton.
Yeah.
If you hold the ball, you dissolve. If you drop the ball, you float.
And this isn't just a party trick. This is exactly how we separate amines in the lab or in industry.
Oh, really?
Yes. If you have a mixture of organic compounds, you add acid, the amine goes into the water layer, everything else stays in the organic layer.
And then you just separate the layer.
Separate them, add base to the water layer, and get your pure amine back.
That's brilliant. What about a technology application? We mentioned nylon earlier. That's a fabric we use every day. How does a hand build a jacket?
Nylon is a classic example of acylation happening over and over again. You take molecule with 2 amine groups, 1 on each end.
A molecule with 2 hands.
A molecule with 2 hands. And you react it with a molecule that has 2 acyl groups, 2 hooks.
2 hands, 2 hooks.
Perfectly said. The amine hands grab the acyl hooks. They form amide bonds. But because both molecules have 2 connection points, they don't just pair up, they chain up.
Right, they link together.
Hand grabs hook, the other end's hand grabs another hook, and so on. Chain after chain after chain. That long chain is the polymer nylon.
So when I wear a nylon jacket, I'm basically wearing a billion tiny chemical reactions where a lone pair grabbed an acyl group.
That is technically correct. It is chemistry in action on your back.
I love that. Now, let's hit a counterintuitive example, something where a student's gut instinct might be wrong.
Okay.
You mentioned earlier that primary amines are usually better nucleophiles because they aren't crowded.
Yes, that is the general rule.
So a student might think primary amines should always react faster than secondary or tertiary amines.
Right, that's the naive assumption. You think less crowd, faster reaction, but actually it's not that simple.
Here is where the examiners like to trap people.
Exactly. Take acylation. Here, steric hindrance. The crowding matters a lot. A bulky secondary amine will react much slower than a primary amine because the hand is physically blocked.
It's hard to reach the hook, so in this case, yes, primary is faster.
Correct. But consider basicity just grabbing a proton. In the gas phase, where there's no water to complicate things, a tertiary amine is actually the strongest base.
Wait, the most crowded one is the strongest. Why?
Because of the inductive effect. Those 3 alkyl groups are pushing electron density towards the nitrogen.
Okay.
They are pumping up the hand, making it super negative, super strong.
So the hand is stronger, even if it's harder to reach.
Exactly. Reactivity is always a tug of war between the strength of the lone pair, which is an electronic factor, and the crowding around it, the steric factor.
You cannot just memorize primaries best.
You can't. You have to look at the specific situation. And if you are in water aqueous phase, it gets even messier because water molecules crowd around the ions.
And that creates that weird order we see in the textbook.
That creates the weird order where secondary amines are often the strongest, beating both primary and tertiary. It's the Goldilocks zone.
That is such a key insight. It's a balance of power versus access.
Correct.
Okay, We are getting close to the end, and we need to make sure our listeners are ready for their Class 12 exams. We need the clarity lines.
The sentences you can write down for full marks.
Exactly. Hit us with them.
All right, get your pens ready or just screenshot your brain right now. Clarity line 1. All amine reactions involve the lone pair on nitrogen acting as a nucleophile or base.
And the tieback.
If you are ever stuck on a reaction mechanism, always look for the lone pair attacking something. That's your starting point.
Great. Next one. This one covers the products.
Clarity line 2. Acylation of primary amines produces secondary amines, while secondary amines produce tertiary amines.
The tieback for that is important, no.
Very important. Remember, tertiary amines do not undergo acylation with acyl chlorides. They don't have a hydrogen to lose to stabilize the product. They just sit there.
Tertiary amines set out the acylation dance.
Right. Clarity line 3. Alkylation can produce a mixture of products.
The messy one.
Be careful here. As we discussed, the product you make is reactive. It can grab another alkyl group. If a question asks how to get a pure primary amine, alkylation is a bad answer.
You'd want something else.
The Gabriel phthalimide synthesis or reduction of nitriles instead.
Right. Okay, what about the aromatic stuff?
Clarity line 4. Aromatic primary amines undergo diazotization to form stable diazonium salts at low temperatures, but aliphatic amines do not.
And why is that?
Aliphatic diazonium salts are way too unstable. They decompose instantly to form alcohols and nitrogen gas bubbles. So if you see diazotization in stable salt, think aniline or aromatic rings only.
And one for the lab practicals, the separation technique.
Clarity line 5. Solubility check. Amine salts are soluble in water, unlike the free amine.
Magic trick.
That's it. Acid makes it soluble, base makes it insoluble. Use this principle to distinguish amines from non-basic compounds.
Brilliant. Those are solid gold. So let's wrap this up with a short summary. If you take away just 3 things from this deep dive, make them these.
Okay.
Number 1, the core idea. It is all about the lone pair. That pair of electrons determines everything, whether it acts as a base, grabbing a proton, or a nucleophile attacking a carbon.
Number 2, the image. Remember the hand. It grabs the ball, the proton, to dissolve, or it grabs the hook, the acyl group, to make nylon.
And number 3, the key distinction. Remember that primary, secondary, and tertiary amines behave differently. It's a complex battle between how strong the hand is and how crowded the hand is.
Absolutely. If you can visualize that lone pair glowing and reaching out, and you can see the bulky groups blocking it, you have mastered Unit 9.
To everyone listening, don't let the mechanisms intimidate you. Just look for the nitrogen, find the lone pair, and ask, what is the hand trying to grab?
Keep revising, keep trying those structures, especially the resonance ones, and good luck with your chemistry.
Thanks for joining us on the deep dive. See you next time.